Okay, folks, so in the last video, we went up to problem 8, and I didn't show you how to do problem 8, but I want to show it here. So let's just look at the problem. It says, compute how many 7-digit numbers can be made from the digits 1, 2, 3, 4, 5, 6, 7 if there's no repetition. Now let's just stop right there. There's 7 digits. And we have 7 numbers, and we have to make a 7-digit number. That means we have to use all 7 of the numbers. So just without even thinking about it too much, 7 factorial would be a reasonable answer. Okay. However, there's a constraint here, which it says all the odd digits must appear in an unbroken sequence. In other words, the odd digits all have to be in a row, and that's a requirement. Now, how can I even think about this problem? Well, let me do the following. So there's 7 digits. How many of them are odd? So odd, 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 odd. So there's 4 odds, and therefore there's 3 evens. Now, how could the answer be expressed? So let me try to see the answer. What are the patterns? Well, I could have odd, odd, odd. Oh, I'm sorry, not 0. Odd. Oh, it's the letter odd. Actually, let me make a capital. O, 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 followed by even, even, even. That would be one form of the pattern of the answer. Or put an even, and then O, 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 and then put the other 2 evens. Or put 2 evens, O, 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 and then put the other even. Or even, 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 O, 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 O. So what I'm doing is I'm writing down the patterns of the answer. Now let's think about, for each pattern, what is the count? So let me think about that. So let me say the count for this pattern, O, 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 E, E, E. What would that be? Well, there's 4 odd numbers. I can put them in any order. So that just arranging the odd numbers, the answer would be 4 factorial. And then the even numbers, it's 3 of them. So that's 3 factorial. Okay, now let's do the next one. Count for E, O, 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 E, E. Well, let's think of them separately. How many ways can I do the odd numbers? 4 factorial. How many ways can I do the even numbers? Well, I can, the first one I pick from 3, then 2, then 1. So that's 3 factorial. So you notice for each of these patterns, there's the same number of ways to arrange the digits to meet that pattern. So total, whoops, yo. So the total, since there's 4 patterns, would be 4 times 4 factorial times 3 factorial. Now you could stop right there. Don't multiply it out, please. But another interesting thing is I could express it also as, because if I have 4 times 3 factorial, I could also write it as 4 factorial times 4 factorial. Now, how did that work? Why did that suddenly become 4 factorial? And the answer is, if you have 3 factorial, and then you have another 4, so then it's 4 times 3 factorial, which in fact is 4 factorial. So for your final answer, you could use either of those expressions, but again, don't multiply it out, please. Okay? So there's some bunch of other problems, but if you sort of think of them in the right way, they'll all come out with answers that look like this kind of thing. All right, so that's permutations. Now the next thing to go into, the next section is they say counting subsets, but the traditional way to say that is called combinations. So if you have a set of elements and you want to pick a subset of a certain size, that's called combinations. I want to take a combination of a certain number of elements from a bigger set. And by the way I think of it is, you don't have to do this, but I'll just say this is a traditional way to think about it, is committees. How many ways can you pick a committee from a certain set of a certain size? And the answer is that there's a notation for it, which is in the book, but I'll just abbreviate it here. Just like in the permutations, we had a formula. Permutations of n things taken k at a time. The formula is n factorial over n minus k factorial. For combinations, how many ways can you take combinations of n things taken k at a time? And you notice the formula here is almost the same. It's n factorial. Here's n minus k factorial, but you also divide by k factorial. And the book goes into a long story about why this is true. We can go into that, but I think I would rather that you just remember this formula and that this can be written down two different ways. One is using the function c and so on, and another is a very old way of doing it, which is you write it almost like a fraction. Don't put the fraction bar in there, and do surrounded by parentheses, and that's another way of talking about combinations. So you're going to see both of these notations. And let me just sort of zip through here because once again what I want to do is get to the problems. Now, here's a very quick summary of one example. How many ways can I choose k, which in this little chart, k is going to have different values. How many ways can I choose k elements from a set that has 4 elements? So 4 is the n in this case. So 4 is what you might think of as the numerator. It's not a fraction, but the 4 is the number on top. And then k is the number on the bottom, and they show you how to calculate it. So how many ways can I pick no elements? Well, you might say 0, but no, actually there's one way, which is the empty set. The empty set is a set that has no elements. So how many ways can I do it? Well, 1, it's the empty set. How many ways can I pick one element? 4 ways. How many ways can I pick 2 elements? Count it out if you want to, and it's 6 ways. But if you do the formula, you'll also get 6. How many ways can I pick 3 elements? Turns out there's 4 ways. And by the way, there's a certain duality here. How many ways can I pick 3 elements? How many ways can I pick 1 element? And the answer is the same answer. And also another way to think about it is if I'm picking 3 elements, then I'm choosing to not pick one of the elements. So A, B, C actually matches up with D. D is the element I didn't choose. A, B, D matches up with C. C is the element I didn't choose, and so on. So it's sort of logical that the number of ways of picking 3 is the same as the number of ways of picking 1. I mean, mathematically it's true, but it's sort of true logically anyway. How many ways can I pick 4? Well, duh, I have to pick the whole set, so there's only one way to do that. And they also, just for thoroughness, say, well, how many ways can I pick -1 elements? And the answer is, doesn't make any sense, therefore the answer is 0. I can't do that. Or conversely, how many ways can I pick 5 elements? Well, you can't. How can you pick 5? You only have 4. So the answer there is, how many ways is 0? Okay, so that's a quick summary of how that works. But again, I'm kind of assuming you've seen this before. You may not have seen it. yesterday, but I'm sure you've seen it. And here they talk about a very extended example, which I'm going to leave out. So here's the formula. And this is the formula I just put in the notes. So n choose k is the way you say it. And that's the formula. N factorial, k factorial times n minus k factorial. And if k is not between 0 and n, then this symbol is actually equal to 0. Meaning you can't do that. You can't pick that many elements. Now here they showed longhand how to figure it out. So 9 choose 4. The actual expression evaluates to 9 factorial, 4 factorial, 5 factorial. Now for me, I would prefer you just leave it this way. Or you could sort of expand it a little bit if you want to. I mean, I'm not saying you can't do that, but to me, there's no educational value in doing it that way. Now here's a pattern that you're going to see over and over. So it says how many 5-element subsets of A have exactly 2 even elements? Well, let's think about it. It has exactly 2 even elements. How many even elements are there? 1, 2, 3, 4. So of the 4 elements, I have to choose 2. How can you take 4, choose 2? Turns out, if you work it out, it's actually the number 6. But you want a 5-element subset, which means I've already picked 2, but now I have to pick 3 more from the odds. So how many ways can I do that? Well, the odd numbers are 1, 3, 5, 7, 9. So there's 4 of them. So I want to wait for it. 1, 3, 5, 7. Sorry, 5 of them. So how many ways can I pick 3 from the 5? Well, the answer is 5 choose 3. If you work out the math, it turns out to be 10. So 4 choose 2 is 6. 5 choose 3 is 10. So how many ways can I pick them all? I would have to pick 4 choose 2 times 5 choose 3. And again, just you can leave your answer in that form if you want to, or you can work it out if you really want to. Okay. That's the story on that. Cards, I'm avoiding card problems. We have to do some card problems. 3.16, I'm going to show you a trick. There's a very nice trick for dealing with this kind of problem. I'm going to defer that to the next tape because it's a little bit of a long story, but it's really nice and you don't have to do any calculation or hardly. Okay, so here's the exercises. So I'm going to stop here on this tape and then we'll do some exercises together.